Around IT in 256 Seconds by Tomasz Nurkiewicz. Episode 32. Cryptographic hash function.
Sometimes you need to split arbitrary objects into a fixed number of groups. For example, storing a record into one out of many database nodes, or saving a cookie in a hash table, or distributing jobs among multiple workers. In all of these cases, you later want to know which bucket or worker was chosen. Also, data should be split evenly. You don't want one node or worker to be overloaded. The above properties are implemented by a so-called hash function. It's an algorithm that takes arbitrary input and produces fixed-length output, a number. For the same input, often called a message, it always produces the same output, known as a hash. Ideally, different messages should produce a different hash. Even better, two slightly different messages should produce wildly different hash. Good hash functions are quintessential to implement efficient hash tables. It's a data structure which allows searching by key in constant time. You simply calculate the hash of the key and then go to the bucket for that key. In a well-designed hash function and hash table, collisions are infrequent, so two different keys rarely land in the same bucket. But can we do better? Can we have a hash function without collisions at all? Theoretically, it's impossible. If the input space is larger than the output space, by definition, two inputs must produce the same output, sooner or later. In practice, we have several such functions. Meet cryptographic hash functions. This special class of functions are designed in such a way that finding a collision is almost impossible, mainly because the output space is quite large. Cryptographic hashes are typically 16, 32, or even 64 bytes long, a 20-digit number. Finding two messages with the same hash is possible, but it requires brute forcing billions upon billions of messages. Impractical. Let's think about practical usages. In the old days of the internet, users' passwords were stored in plain text in the database, next to username. That sounds obvious. How would you make sure that the password is correct without storing it? The user enters the username, password, and you make the inequality check. Sure, but if your user database leaks, all passwords are known to an attacker. Not only the criminal can log into your account, most likely you used the password elsewhere, so all your services are exposed. But what if instead of storing the password, we only store a cryptographic hash of the password? When a user logs in, her password is hashed using the same algorithm. If hashes match, they must have been produced from the same password. Otherwise, the password is incorrect. Remember, for practical reasons, two different passwords will never produce the same hash. Also, it's impossible to figure out what was the password knowing only the hash. Another use case is verifying the integrity of a large file. Suppose someone sends you 1 GB of data. How do you make sure the file was not corrupted or modified by a malicious man in the middle? Well, if the sender of the file also provides a cryptographic hash of that file, you can verify that file against the hash. Hash is short enough to be provided through a different, more secure channel. We can even go further and hash a message together with our public key. Without going into details, this not only proves that message wasn't tampered with, the digital signature also proves we are the authors of that message. Thanks for listening. Bye.